can't review the entire section, but let's review the critical things that we did. So we had a definition that Zi, S is a string, Zi of S is defined as the length, so it's a number, of the longest substring of S starting at position I that matches a prefix of S. So major definition that we were using last time, and last time I showed that if you have these values for a string S, then you can use them to solve the pattern matching problem, the problem of finding all occurrences of a pattern inside of a text. And if you can accumulate these in linear time, in time proportional to the length of S, then you can solve that pattern matching problem in linear time as well. So we were looking at the algorithm for actually finding all the Z values. And so this is the algorithm, this is the Z algorithm for finding all the Zi values. Okay, so I won't put S in there because it's understood. And we're going to do this for I equals 2 to the length of S. So first we'll compute Z2 and then Z3 and so on. So for I equals 2, Z2 is found just explicitly. That just means here you are at position 2, here's a position 1. You want to know what's the length of the longest substring that begins here going forward that matches a substring that begins here. So you just look at the character position 2 and the character position 1. If they're equal, you move on and so on until you have a mismatch. And that tells you what the length of the longest, that tells you what the length of the longest substring starting at position 2 is that matches a prefix. And that's what Z2 is. Okay. So in general, assume we've already computed, we know Z2 up through ZK minus 1, and now we want to compute ZK. So we're going to have some cases based on where K is relative to R. So R was a programming variable that we discussed last time, and let me just draw this picture. As you're going along, computing the Zi values, there are places where the value of Zi is bigger than 0, and they define what I called last time a Z box. And as the algorithm proceeds, there's a rightmost point that's contained in any of the Z boxes. There's a rightmost point that's contained in any of the substrings that we found so far that match a prefix. So R is the rightmost point in any Z box, and its the corresponding leftmost point of that Z box is L. Actually, L we only need, or you only need, one only needs if you're programming. You need that to figure out some of the other variables. But if we're just drawing pictures and talking about things at a higher level, we won't really need L explicitly. So everybody remember what R is? I'm not writing down the definition, but I've just told you it in words. Again, last time we wrote it down very explicitly. So in general, when we want to compute ZK, we have cases based on what K is relative to R. And so the first case, case 1, is that K is strictly bigger than R. So in this picture, we might be out here, K. So K is not contained, position K is not contained in a Z box. There's no match we found so far, no starting position we found so far that extends a substring to K or beyond, matching a prefix. So when K is bigger than R, then we compute ZK explicitly. Okay? So again, that's similar to the case of Z2. We're just going to do that by direct comparison, and obviously there's no issue about correctness when that happens. So case 2 is when K is less than or equal to R. So here we're in this sort of picture. So R is here, and so we'll make this bigger because we're going to it gets a little bit messy. So this is K, this is R. All right, so this was the case when K is less than or equal to R, and so that means that K is inside of a Z box. Why do we know it's inside of a Z box? Well, the right end of the Z box is greater than or equal to K, so it's further to the right. And the left end of that Z box was established when the algorithm was computing a Z value previous to the point where it's trying to establish or compute the ZK value. So that means it has to be somewhere to the left of K. So K is actually inside of a Z box. So position K is inside a Z box. Okay, so if we give this string here from position L to position R, if we give that a name, we'll call that, or giving it a name, we'll call that alpha. This chalk is, we'll give that the name alpha for that entire string, and for this portion of it that goes from position K to position R, we'll give that a name beta. Okay, so we have two strings there. Now there are two other occurrences of alpha and beta that we know about for sure. Because this is a Z box here, this is a substring that occurs as a prefix of S. So alpha has got to be there at the beginning. So that's alpha. And the corresponding distance in here, that's about right. That's beta, and I'm calling this position K prime. Okay? So if you were writing a program, you'd have to figure out what K prime is, but you can certainly do that knowing L, R, and K. Okay? That's a programming type detail. So we know what K prime is, and we know that there's a beta here. Okay? And we know already ZK prime because the algorithm computes the Z values left to right. K prime is definitely less than K. So we know what ZK prime is. And so in case 2, there are going to be two cases. Now, I may be deviating a little bit from what's written in the notes. The notes are written in one way, and after several years of presenting this, I think there's a somewhat better way to present it, which breaks up the cases a little bit differently. But either way, it'll make sense. It should make sense. So, but here we are. Case 2a is that ZK prime is strictly less than the length of beta. Okay? So we know K prime. We're trying to compute ZK. We know K prime and ZK prime. We're trying to compute ZK. We can look up ZK prime. We know what beta is, and so we know its length. And in case 2a, the length of ZK prime is less than the length of beta. So, all right, let's try to draw this a little bit. So here was beta. This whole thing is beta. And let's say that the portion of it that defines zk prime, that is the longest substring that begins at position k prime that matches a prefix, defines the substring gamma. Okay? Gamma, the length of gamma is definitely less than the length of beta because zk prime is less than beta. So that means that there's a gamma right here at the beginning. Okay? Everybody with me on that? All right. So, and where's another gamma, by the way? Yeah.
Right after K?
Yeah, right after K, because this is beta. It matches this beta, and this beta has the gamma at the beginning. So we can, this was beta, and then we have gamma over here again. Okay. Now, let's consider the next character here. Let's say this is x. Okay? So the next character just after this gamma is x. What's the character here? Something not x. That's all we know. It's y. Let's give it a name y. Where y is not equal to x. Now, how do we know that y is not equal to x? Well, if y had been equal to x, then the substring starting at k prime that matches a prefix, the longest substring wouldn't be gamma, it would be gamma plus that extra character at least, maybe even beyond that. So this next character here and here, those two characters can't match. So y is not equal to x. Okay? Now what's the next character here? It's what? I hear x. Anybody else vote for x? I hear 2 x's, 3 x's, 4 x's, 5 x's, 6 x's. All right, one after another. Okay, so that's an x. And again, the reason this whole beta, the whole beta here, matches that whole beta there. Okay? So that's got to be x. And since that's x and this is y, where y is not equal to x, what we can see by this picture, we've deduced that starting at k, there is a substring, namely gamma, that starts at k and matches a prefix, gamma, but the next character over, those two characters do not match, because the next character over here is y, where y is not equal to x, and the next character over here is x. So this line of deduction shows us then that in case 2a, when zk prime is less than beta, then we know that zk is equal to zk prime. Right? So in the algorithm, in the case when k is less than or equal to r, okay, we know what k is. It's less than or equal to r. We can use k, r, l, whatever, to figure out what k prime is. We look up zk prime, and if we find that the length of zk prime is less than the length of beta, and we know what beta is, that's this length, then zk is equal to zk prime. So in this case, no character compares are needed. Okay? We do some constant amount of arithmetic. We have to figure out what k prime is. Then we do a lookup. We have to look up what zk prime is. We have to then compare it to the length of beta. But these aren't character comparisons. And that's clearly a constant amount of work unrelated to the length of the string. It's a constant that's done at each position where we're in case 2. Okay. So in this case, no character comparisons are needed. Constant number of other ups are needed, are used. So that's really a great case, because we said our primitive operation was character comparisons, and this is a case where we do 0 character comparisons. If we could do that at every position, the algorithm would do 0 work. Of course, anyway, I don't want to get into too weird a comment about that. At any rate, that's case 2a. Okay, zk prime is less than the length of beta. Now, this is where I think the organization that I'm doing of the algorithm that I'm doing in class is a little bit different than what's in the notes. But either way, it should make sense. Case 2b is zk prime is strictly greater than beta. Okay? I think in the notes we have zk prime greater than or equal to beta. But here now I'm going to break into 3 cases. Zk prime is strictly less than beta, strictly bigger than beta, and then we'll look at equal to beta. Okay, so let's think this one through. Zk prime, let's see, can I reuse that picture? It's getting very cluttered. I'll just redo it. Okay, so here's alpha again, here's k, here's beta, here's k prime, another beta, another alpha. All right, so zk prime is strictly bigger than the length of beta. That means starting from position k prime, there's a substring that definitely goes beyond that beta there. And again, we'll call this, I don't know if we need a name for it, but we can call it gamma. And that means that this gamma occurs as a prefix here. So that's gamma. That's gamma. Okay, so that occurs as a prefix. All right, now what can we deduce? Well, let's look at this character and this character. Well, this one, let's call this x again. All right. What is this character?
Not x.
Not x. Who said that? And why?
Well, because we know that the alpha on the right only matches the prefix at the beginning up to that character x, and that character x has changed as different because it's a z-box.
Right. We know this alpha matches this alpha, but that's the longest match starting from this position, starting from L. The longest match of a substring that matches a prefix, largest match that starts at L and matches a prefix. Therefore, if the next character here is x, the next character over here cannot be x. Otherwise, that would violate the definition of longest. So that has to be y. Okay? So I guess I should have used gamma for this part. It doesn't matter. So now, this little piece in here, okay, let's call that delta. Yeah. This picture is getting too cluttered. That's gamma, so delta is about there, okay? Everybody comfortable with that picture? If you are, tell me where there's another delta. Stephen.
Over on the right side with beta.
Okay.
On the far right.
Oh, yes. Okay, then tell me, did I need to label it delta? Yeah.
It's just beta.
It's just beta. Okay. The picture's getting too cluttered. Yeah, the thing I labeled as delta is actually just beta. Okay. Anyway, nothing wrong with giving it another name. It's just that's beta, and this is beta. We already knew that. Okay. So this is y, this is x. Where's another y? Yeah. After the first beta, that has to be y, okay? Because this whole thing is gamma, right? And gamma is over here. Gamma is bigger than beta, right? And the next character over here was y in this copy of gamma, so it's got to be y in that copy of gamma, okay? So right after this beta is a y, and we already know that y is not equal to x. Right over this copy of beta, that was beta right there, is an x, okay? So what do we conclude from all this? Starting from k, we have a substring, namely beta, that matches a prefix of s, namely beta. The next character over is a y, and the next character over here is an x, where we've concluded that y is not equal to x. So the conclusion is, yeah?
Zk equals magnitude of beta?
Yeah. So zk, in this case, this implies that zk is equal to beta. Okay? And in this case, how many character comparisons did we do? How many times did we look at individual characters in strings and look to see if they're equal or not? Yeah.
None.
Yeah, again 0. Okay? So in this case, the algorithm does 0 character comparisons. So that's also a very good case because, again, character comparisons are primitive operations, and we don't have to do any in this case. Of course, again, it does a constant amount of other operations. The same as in case 2a. It has to decide, has to figure out k prime, look up zk prime, decide it's in case 2b, and then it's finished. Okay? So in case 2b, the algorithm doesn't have to do any character comparisons either. Okay, let's do the final case, which is case 2c. All right. Well, we've looked at the case where zk prime is less than beta, and the case where it's strictly larger than beta, so the only case that's left is zk prime is equal to beta, length of beta. Zk prime is equal to length of beta. Okay, I could redraw everything, but if you just go back over to here, let's see if we can just modify this picture. All right, so I'm making the cameraman do a lot of work here, and the people watching this are going to get dizzy. Okay, so now zk prime is strictly equal to beta. All right? We'll get rid of that. It's equal to beta. So zk prime equal to beta. Okay. All right, that means that starting at k prime, the longest substring that matches a prefix is of length beta. Now these kind of got out of scale. I'll just try to fix that a little bit. This is beta, that's beta. There. Okay. Now, what can we say about these two characters? Same or different? They've got to be different because we know that the length of the longest substring that begins at K prime that matches a prefix is just beta. All right? So let me label this. I'm going to use something new. Like, let me label that P. Okay? And this one is Q, where P is not equal to Q. Right? So we got that. Now, this gamma still matches that gamma, okay? And therefore, starting at K, there's still a match of, this is still beta, which matches that beta, and therefore, of course, it matches that beta. So we see that ZK, what can we say about ZK at this moment? The length of ZK is at least the length of beta. Okay? It might be longer, but so this is now case 2C, where ZK prime is equal to length of beta. Okay? So we know just from looking at this picture that ZK, its length is greater than or equal to the length of beta. All right? Now the next character over here is still an X. Okay? What do we know about X compared to P or compared to Q? Yeah?
X is not P.
X is not P. Good. X is not equal to P because the length, this was alpha, the longest substring that matches a prefix. So definitely X is not equal to P. But what do we mostly care about in terms of computing ZK? We know that starting from K, we have this substring beta that matches a prefix. And the next character over here is Q, and Q is not equal to P also. So we still have the possibility that X could be equal to Q. Okay? So X equal Q is possible. We haven't found any reason why X should not equal Q. We know it's not equal to P. We know P is not equal to Q. So X is not equal to P and P is not equal to Q. So that's some small evidence that maybe X is equal to Q. All right? But we just don't know. And there's no deduction here that can resolve that. So what should the algorithm do at that point? Well, so far in case 2, the algorithm hasn't done any character comparisons. And so, it did do some character comparisons in case 1. So it's not as though the algorithm doesn't do any character comparisons yet at all. But still, it seemed like the algorithm should be doing some more character comparisons. So what happens in this case, in case 2C, it knows that starting from K, it matches the beta. There's no reason to look inside there. That's already known. But from that point on, you do explicit comparisons. You compare this character X to this character Q. If they're not equal, then ZK is equal to beta. But if they are equal, then ZK is equal to at least the length of beta plus 1, and you move on and do the next comparisons. And if they're equal, you move on and do the next comparisons and so on. So you do explicit comparisons until you find a mismatch. And at that point, you know what ZK is. Okay? So in this case, do explicit comparisons. Explicit compares from positions. Well, it's R plus 1 and beta plus 1. start there, until a mismatch is found. And then zk is known at that point. Okay? So that's the algorithm. In case 1, when k is greater than r, we do the explicit comparisons. In case 2, we only do explicit comparisons when we're in case 2c. And we also had the beginning case, well, when I was equal to 2. You can think of that as a case 1. If you just think of r starting at 0, then when you're looking for z2, k is equal to 2, so k is bigger than 0, and you just do explicit comparisons. So that's the whole algorithm. And it should be clear that it's correct. Certainly, when you computed z, in case 1, it's certainly correct because you're doing the explicit comparisons. Nothing. In case 2a and 2b, we went through the arguments that showed that we could compute zk without doing any explicit comparisons. In case 2c, we argued that this first portion, beta, was equal to a prefix in beta, and from that point on, you're doing explicit comparisons. So again, it's clear why that's going to be correct. So if you follow the core of the argument, which was the case 2a and 2b, and also this deducing of the beta here into C, then again, correctness should be no issue. Any questions on correctness or why this actually computes the z values correctly? Okay, well, let's do time analysis. So time analysis. So here's a claim. The algorithm does, at most, order S character comparisons in worst case. Okay. So this is this is sort of a style of argument that's sometimes called a bouncing ball argument, where you just watch some variable that's represented by a ball moving as the algorithm goes along. Well, I'm embellishing that too much. Although you can find animations that people have done for various algorithms, and sometimes they illustrate the algorithm in that way. But at any rate, as the algorithm goes along, we're just going to focus on variable r. Okay? So variable r only increases, never decreases. There's nothing in the algorithm that decreases r. I guess I should have made one more point explicit. We defined r as the longest, as the rightmost position that's in any z box. Okay? When do we ever extend a z box? When do we have create a new z box? It's in case 1. If k is bigger than r, and we're doing explicit comparisons, we might actually create a z box at that point. I'll just, well, over here, here's r, here's k. And so this is case 1. So k is bigger than r, and suppose that we actually find that zk is strictly bigger than 0. Then what happens to r? We created a new z box here. R gets moved over, right? Because the rightmost position is now further to the right. After all, k was further to the right, and the rightmost position is to the right of k. So in case 1, if we actually find some matches, if we find matches, then R will move to the right. Okay? What happens in the case of case 2A? What happens to R in case 2A? Nothing. It stays the same, right? Because it was, just to redraw that, here was R, here was K. We found that ZK ended up inside this box, so R remains the same. What happens in the case 2B? 2B got erased. Oops. Anyway, what happens in 2B? Remember, in that case, ZK was equal to length of beta. What happened to R? Nothing. Right. It stays the same. What happens in the case 2C? What happens to R? Yeah.
It potentially moves to the right?
It potentially moves, yeah. You're going to compare this character to this character. If it's a mismatch, immediately R stays the same. But if it's a match, then R moves out by at least one position. And the important thing to observe here is that the number of positions it moves to the right is exactly equal to the number of matches that get made in this case. So if we have one match, then R moves one position to the right. If we have 6 matches, it moves 6 positions to the right, and so on. But in none of the cases does it ever move to the left. So R only migrates to the right, and the number of positions it migrates, so in any iteration, R stays the same or moves to the right, moves to the right by an amount at least as large as the number of matches. Okay, so whenever you're comparing two characters, either they mismatch, they're not the same, or they match. We do comparisons in case 1, and if we have any matches, R moves to the right at least by the number of those matches. It can actually move to the right more than the number of matches because K was strictly bigger than R in case 1. So it's going to, let's say we had 5 actual matches, R is going to move to K plus 5, right? Or minus 1, whatever. But the point is then R will move at least 5 positions to the right. And in the case 2C, R moves exactly to the right by exactly the number of matches. Okay? Not comparisons, matches. All right. So in any iteration, R either stays the same or moves to the right by an amount at least as large as the number of matches. So we're trying to count the number of comparisons. So also, in any iteration, the iteration ends. Oh. In any iteration where there are some comparisons are done, And remember, in some iterations, there are no comparisons done at all. Those are the cases 2A and 2B. There are no character comparisons. But if there are character comparisons that are done, then the iteration ends when the first mismatch occurs. Okay? The character comparisons are done in case 1, and you're doing the explicit comparisons, and as soon as there's a mismatch, the iteration ends. Or they're done in case 2C, and again, you're doing explicit comparisons, and the first time there's a mismatch, the iteration ends. So each iteration has at most one mismatch. So we can bound the number of comparisons in the entire algorithm. How many comparisons are mismatches? Well, how many iterations are there? There's one iteration for each position in the string. So there's S, the length of S iterations. And at most one mismatch per iteration. So this thing implies the number of mismatches is less than or equal to the length of S. Okay. This many iterations, at most one mismatch per iteration, so certainly at most that many mismatches. Every comparison is either a match or a mismatch, so we've already bounded the number of mismatches. Thinking over here, how many matches can there be in the algorithm? Every match, every time there's an iteration that does a comparison that has matches, R moves to the right by an amount at least as large as the number of matches. Okay? R never moves beyond the length of S. R never moves to the left. So those statements altogether imply that the number of matches is bounded by S also. Okay? So this over here implied the number of matches is less than or equal to S. Every comparison is either a match or a mismatch, so we actually have shown that the number of comparisons is less than or equal to 2S. Okay? And what we claimed over here was that the algorithm does at most order S character comparisons. So we've certainly done that. In fact, we have a nice constant here, which is 2. The number of character comparisons is bounded by twice the length of S. And you can even do, I think you can do even a more refined analysis. So at each iteration, the algorithm does some constant amount of other operations besides character comparisons, a fixed number of them. We could count them up. 5, 10 is certainly a bound on what they would be. 10 is too much, but anyway, some fixed number of operations besides character comparisons, totally independent of the length of the string. And the number of character comparisons it does is at most 2S, two times the length of S. And so altogether, the total work in the algorithm is order S, order the length of S. So the algorithm does at most that many character comparisons. So the time for the algorithm is order the length of S. And that's the heart of it. That's the crux of it. You can compute all the Z values in linear time in the length of S. And we previously, last time, talked about how if you have an algorithm to compute all the Z values, you can do the pattern matching problem. You can find all occurrences of the pattern inside the text in the time it takes you to compute all the z-values, and therefore you can solve the pattern matching problem in linear time. Okay. The fact that you can solve it in linear time was considered a great result, I think, in the early 1970s, and as I mentioned last time, Knuth Morris Pratt KMP algorithm was the first algorithm to establish that fact. But the Z algorithm, I think, is more accessible and has other applications besides pattern matching, because you have this general algorithm for finding Z values. Okay. Questions on that, or the great result of 1973? I mean, okay, that was 37 years ago, but it's still a great result today, the fact that you can do this in linear time. So I've got about 5 minutes. I'll just show you one more thing that you can do with strings, just a sort of a cute example of cleverness, ways people can be clever in string algorithms. And this is often a homework exercise. This is often given as a homework problem, but it's been used so often that it's sort of used up at this point. So you're given a string S and a string T. And you want to know if S is a rotation of T. So what do we mean by rotation? Let's say S is equal to AB, X, Y, Z, Q. All right? And T is equal to Y, Z, Q, AB, X. So you can create S from T by doing a circular rotation. X comes in the front, then B comes in the front, then A comes in the front. And you've rotated. If you think of these as circular somehow, you do a circular shift, then S and T are just related by circular shifts, right? Okay. Now, if you think of a straightforward kind of direct algorithm for this, if, let's say, the length of S, length of T is equal to, well, certainly if the length of S is not equal to the length of T, then you know that one isn't a rotation of the other, and you can stop. But if the lengths are the same, then one thing you could do is explicitly create the circular shifts one position at a time, one character at a time, and then do your comparison. But if you did that, the time bound, the explicit time bound then would be, worst case time bound would be order n squared, because there are n different shifts, and if for each shift you're going to explicitly look at the two strings, then and you have to count order n worst case time for that comparison, and so that's going to look like n squared worst case. But I claim that this can be solved in order n time. By a clever reduction to just basic pattern matching. Does anybody see how to do that? Yeah.
Run the Z algorithm on $$ $TT.
Okay, let's do that again. Run the Z algorithm on what?
$TT.
$$ T.
And T again.
And then T again. Okay. And what do you do when you run the Z algorithm on this?
You check to see if you get a Z value equal to n.
Okay. So run Z algorithm on that, S followed by $TT, and look for any ZI equal to the length of S, where I is bigger than, well, bigger than 2 works, but in fact it's okay to say I greater than or equal to S plus 1. And that's correct. That will work. There's a slightly simpler way of framing it, but this is essentially right. And it is right. And I'll let people think about why that's true. And certainly it's linear time because this string here is the length of S plus twice the length of T plus 1. And so we can get all the Z algorithms here in time linear in N. Okay? It's kind of a neat little algorithm there, a way of using linear time pattern matching to be able, or in this case Z algorithm, to be able to. So another way of saying this is look for any occurrence of S in TT. That's just another way of saying it. If you find an occurrence of S in TT, then S and T are circular rotations of each other. If you don't find an occurrence of S in TT, then they're not. Okay.